I'll just copy that number. Peter's algorithm, to handle 3 elements in the array, he will need 3 comparisons to confirm that an element is not in the array. Okay? Because if this is linear search, the value that I'm looking for may be greater than the last one. So Peter's algorithm may potentially need 3 comparisons. So the amount of time that he would need is 3 times what he had before, which is still a very small amount. That's still a very tiny number. So the next one up is 7, because I only go by 2 to the power of something minus 1. Then 7 is the last one. I will need 3 comparisons and 3 units of time. Peter's algorithm is proportional to this number here. So from now on, I would just say that that is the same as that number. And his algorithm will take this much time compared to my algorithm. Is that okay so far? So I'm not going to bore you with a whole bunch of numbers in between. We'll just kind of jump to 255. In 255, which is 256 is 2 to the power of 8. So that means I need 8 comparisons to confirm a value is not in the array. And consequently, it will take me, whoops. Okay, I thought I changed that to refer to the value. Yes, I did not do that. Okay, Peter's algorithm is also fairly easy to figure out. It will take exactly 255 iterations in the loop, and it will take exactly this much time to finish the calculations. And you can see that I'm still losing big time. Okay, it takes me 8 units of time, and Peter's machine will only take about 4 milli of the same unit of time. And that's still a big, huge difference between the 2 approaches. So we'll jump a few steps and go to 4095, which is 2 to the power of 12. Okay? So in this case, my algorithm will take exactly 12 iterations, taking 12 units of time, and Peter's computer will take 4095 iterations and taking 0.06 units of time. Now you can see that the gain that he had earlier is starting to erode away. Very slowly, but it's starting to erode. So next up, we'll go for another power of 2. Let's say 65535, which is 2 to the power of 16 minus 1. My algorithm will require exactly 16 iterations, and Peter's algorithm will require 1 unit of time. My algorithm requires 16 units of time, so I'm still losing. Okay? When do you think I will start to when do you think it will break even? We double it one more time. I don't think doubling it one more time I will win just yet. Well, okay, instead of me doing the calculations, I'll use the spreadsheet to do it. Yeah. So that seems reasonable. So let's move to 2 to the power of 24. So my algorithm will take exactly 24, and we'll go figure out how much time Peter's algorithm will take. Peter lost. Yeah. And then Peter came back and complained to the boss and say, that is just unfair. Tech should have used a 286 computer instead of a 386. Do you think that would change anything? It would just change the break-even point. Why is that? I mean, how can Peter have lost in this race? He had top-of-the-line fast computer that is more than 65,000 times faster than mine. How could he have lost? When he had a clear winning initially, okay? Don't forget that he was winning initially big time. So how could he have lost this race? If you plot the 2 curves, what do you see? If you plot the amount of time it takes,
yours is steady growth.
Yeah, yours is linear almost, and his is.
Mine is actually no. His is linear to the. Okay, if I plot one axis, the x-axis, as the number of elements in the array,
Right.
and the y-axis as the time that it takes to complete.
Right.
His algorithm, Peter's algorithm, is a straight line, just like that. My algorithm, on the other hand, is a log line. Okay, it's a log line. So initially, I might be like this, but eventually my curve will almost approach a flat line. In other words, it doesn't matter what is the constant that I multiply to scale it up. In other words, you can stretch my curve up like this to slow me down initially, but because of the shape of this curve, I will eventually catch up with Peter.
So this is a lesson basically in knowing how big your array is supposed to be when you start out in order to determine what sort of methodology you're going to use to find an element within that array. And if you've been working for a company that only supplied 255 products and you had to search an array in a database for two, you'd be gone. And Peter'd still be there. But on the other hand, if you have to search 500,000 customers in the United States of America, or let's say 50 million customers, you'd be there and Peter'd be pumping gas someplace. Okay.
But the key is the shape of the curve. Okay?
Right, but it's also knowing what you have to deal with that helps you determine which
one you should
use.
Basically,
Right?
basically the time that my algorithm needs to take is proportional to the log of the number of items in the array. Approximately. It's not exactly that, but it's close enough. Okay? Peter's algorithm, on the other hand, is proportional to just bar A bar. Okay? Now, proportional means that I can find a constant k so that t tac equals to k times log of bar A bar, and Peter's time is proportional to some other k, k2 times bar A bar. Okay? And that means, I will catch up eventually. It's just a matter of how big of a bar A bar do I need before I start to catch up. Okay? Now, this is called the complexity or the time complexity of an algorithm. Now, it is a big deal because, in this case, it determines who gets to keep his job. Okay? And when you read up, I just want to spend, just a few more seconds to talk about this because it is a very important concept. This class is a little bit early for any exposure to the calculations, to the math of it, but not to the concept of it. Okay? So if you go to Wikipedia, now most of the time you don't have to write your own algorithm because Wikipedia has almost an algorithm for just about anything that you can think of. So if you look under algorithms like linear search, yeah, it's kind of sleepy. Too early in the morning. Okay. So if you look under this, you can see the big O notation, and it says that it has a time complexity of big O of n, and n in this case is the size of the array, which is our bar A bar. Then you can look up binary search. When you look up binary search, it will list its worst case performance. The worst case performance is the big O of log n. And remember, n is bar A bar. Doesn't that kind of relate to what I talked about here? Yeah. Okay? So the big O notation, at least at this point, is really just kind of saying the algorithm will take an amount of time that is proportional to blah. Okay? The constant that you multiply to this number here is irrelevant because it does not change the shape of the curve. So what you need to do when you search or when you are looking for an algorithm to solve a problem is you want to search for an algorithm that has a function inside the big O that grows slower. The slower it grows, the better. And log of n grows very slow compared to n itself. Yep.
But if you're going to compare it to computers, then the binary is going to be a lot faster, right?
Sorry?
If the power of the computers will be equal, then the binary is going to be a lot faster, right?
Yes. Yep, absolutely. Okay, well, that's all I want to talk about today, and I'll see you guys next Friday, and the homework will be up. I will work on it. I will make sure that you guys get homework.
We got homework.
You will. You need homework. Homework is good.
So where should I look for that? I got another one. I thought about it a long time ago, but you brought it up in class today.
Say again?
The Bluetooth.
You need to look. You need to find a Bluetooth chipset that is inexpensive.
Well, where would I look for something like that? You're the man.
I have not looked into that particular,
Because I remember
thing.
you showed me that one site to find cheap, power supply chips that don't use too much power, but can provide